The Curry-Howard isomorphism is a result linking computer science to formal logic. It is often stated as the following equivalence: propositions correspond to types, and proofs correspond to programs. But how is this the case? How could something like an integer or a function from an int to a string be interpreted as a logical statement? And how could a program be equivalent to a series of logically justified steps? In order to answer this question, we first need to reframe how we think of propositions. We will turn to a form of logical reasoning called intuitionistic propositional logic, which is concerned with proofs that are purely constructive. A constructive argument is one which demonstrates the truth of a statement by providing direct evidence for it. We normally think of propositions as containing logical variables that can either be true or false, as well as by logical connectors which join them. In intuitionistic propositional logic, however, we instead consider variables that loosely represent the idea of evidence. How might we interpret the implication connective with this new evidence-based way of thinking? One way is to treat implication as a function that transforms evidence for one thing into evidence for another thing. Thus, A implies B can be interpreted as a function from A to B. In programming, we consider variables as evidence for their corresponding type, and a function as evidence for an implication. For example, the function f of x equals x, where x has type A to A, and serves as evidence that A implies A. We now turn ourselves to the second question: how do programs correspond to proofs? In order to do this, we need another framework for logical reasoning using intuitionistic propositional logic. This framework is called natural deduction, and is a system of inference rules for deriving conclusions from a set of premises. The main inference rules we will be looking at are modus ponens and implication introduction. Implication introduction doesn't have an easy equivalent in classical logic, but it basically says that if P provides evidence for Q, then P implies Q. Now, to see how this links proofs with programs, consider a simple program written in a made-up typed language. This function takes in two arguments. The first is a parameter, and the second is a function. It then returns the result of the function applied to the parameter. In order for this to run properly, the type checker has to verify that the types are used in their correct contexts. It checks two things. If a function has type A to B, and it is applied to a variable of type A, then the result of evaluating it will be of type B. Secondly, if a variable has type A and another variable has type B, then any function which takes in the first and returns the second has type A to B. Since x is of type A and g is from A to B, g can accept A as an input, and the result of evaluation is of type B. So the type signatures check out and the program is valid. Note, however, that we have already identified that functions between types are equivalent to implications, and so the first rule says that if A implies B, we have evidence of A, then we have evidence of B. This is exactly the inference rule modus ponens. As an exercise, you can verify that the second type checking rule is equivalent to the second inference rule. Remember that variables are equivalent to evidence for the type that they inhabit. With this in mind, the program becomes a demonstration of the inference rule modus ponens. X has type A becomes we have evidence of A. G has type A to B becomes we have evidence of A implying B. And G of X becomes equivalent to applying the rule of modus ponens and concluding B. Thus, the Curry-Howard isomorphism is a result demonstrating that by thinking of logical reasoning as a way of manipulating evidence, it is possible to link propositions to types in programming, and, in addition, the rules of inference for this method of reasoning are equivalent to performing type checking on expressions within a well-typed programming language.